So, in my previous lecture, I have discussed about different types of well foundation and how we can determine the depth of well foundation. I have discussed about the scour depth, maximum scour depth, then the grip length, and then ultimately the depth of well foundation. Now, today I will discuss that how we can determine the thickness of the concrete seal in open caisson or well. So, as in my previous lecture I have already discussed that when the bearing strata is reached for open caisson, when the concrete is poured inside the shaft under water to seal at the bottom. So, that means here you can see. So, this is the shaft and these are the placed where the concreting is done to seal the bottom, and then once the concrete hardens, then the sand, the shaft is filled with the sand or the concrete, and then the further constructions are done. So, that means once this bottom seal is done, so you have to check whether that thickness of the concreting for the bottom seal is sufficient or not. So, why this thickness is important? Because in that case there will be a buoyancy force which will act in the upward direction. So, that concrete is sufficient to take care that buoyancy force or not, that we have to check. Because in that situation we will not consider the weight of the water which is inside the shaft, because we do not know what would be the depth of water inside the shaft. So, it is better to neglect that weight. So, we will consider only the concrete thickness weight to check that it can stand against that buoyancy force or not. So, here that thickness here in this figure you can see this bottom plug or this concreting, that thickness we have to determine. Or if I draw a separate figure to calculate that thickness. So, this is the shaft and here the concrete is done. Okay? And suppose that thickness is this one. So, this portion of thickness of the concrete seal we have to determine. So, this is the water and this is the scour level or this is the HFL. This is the center line. So, this one is the scour level, scour depth or maximum scour depth, and this is the HFL. Okay. And say this one is the depth of foundation below the scour level, and this is the T thickness of the concrete seal that we have to determine. And we have two diameter of the shaft, one is the inside diameter, another is the outside diameter. So, this is say R I inside diameter and this is R O outside diameter, radius R we are giving it. So, that means this is a radius. And suppose there can be two types of well, those are commonly used. One is the circular cross section. So, this is the circular cross section, which is the section that I have drawn. So, this is for the circular cross section or circular well. So, this one is the inner radius I R and this one is the outer radius I O. So, it can be a rectangular cross section also. Okay. So, it can be a rectangular cross section also. So, this is the rectangular cross section of the well, and where this is L O or L outside, this is L inside, this is B outside, and this one is B inside. So, outside width, inside width, outside length, inside length. So, these are the particular well. So, for which we have to determine the thickness of the bottom seal. So, the thickness of the concrete well or seal, that is equal to T as for this figure, this thickness, or here you can see this thickness, where this is the also thickness of the bottom seal. So, that we have to determine. So, I have drawn a simplified section. So, it is a circular either or it can be rectangular, but this section corresponding to this one, these are the two sections. So, this is the plan, circular cross section, and this is the section, and this can be rectangular also. That means, but the section that I have drawn, the section figure is for the circular cross section, okay, but it can be rectangular also, that I want to say. So, now that thickness of the concrete seal, that will be equal to 1.18 R I inside radius root over Q by F C. Okay. That is for circular cross section. Okay. And it can be T is equal to 0.866 B I root over Q divided by F 1 plus 1.61 L I divided by B I, that is for rectangular cross section. Cross section or rectangular section. Now, where R I is the inside radius of the circular cushion, circular well or the cushion, Q is equal to the unit bearing pressure or unit pressure at the base of the well or cushion. F C is equal to allowable concrete flexural stress, that is equal to 0.1 to 0.2 F C dash. Now, where F C dash is equal to 28 days compressive strength of the concrete. Okay. Similarly, the B I and L I, B I and L I are the inside width and length of the cushion for a rectangular cushion. Okay. So, this way we can determine what would be the thickness of that concrete seal, and this depth D is the below the scour level. Fine. So, now next what is how we can calculate that. So, for the or here I can write one more thing, that Q is equal to here. So, okay. So, in this equation the Q is roughly we can write that there will be a, that means Q is the, in this base what is the pressure which is acting here. So, what are the pressure which is acting at the base? The downward stress that is acting due to the concrete seal, and the upward stress which is acting due to the buoyancy force. Okay. So, the net stress which is acting at the base of this well, that is equal to Q. That means the stress or bearing pressure, or you can say the pressure which is acting at the base, the net pressure. Okay, so, that means here the net pressure, as I mentioned, there will be a buoyancy force that is acting in the upward direction, and or the buoyancy stress or the pressure due to the buoyancy, and there will be a pressure due to the concrete seal self weight. Okay. So, that means we can write that the Q is roughly is equal to the buoyancy stress due to the buoyancy will be H into gamma W, and minus the T is the thickness of the seal into unit weight of the concrete. Now, what is H? H is the total water height from the HFL to the base of the well. So, that is total 1 is equal to H. Okay. So, that is the height of the water at the base of the well. So, that means here this is the height, and this gamma W is the unit weight or unit weight of the water, and this is gamma C is the unit weight of concrete. Okay. So, this way once we know the Q and F c will get from the 28 days compressive strength of the concrete, then we can determine the thickness of the well. So, or here the thickness again I should write. So, this will be the thickness of the well for this particular figure, and here this is the thickness of the well. And here also we have internal diameter and the external diameter also. It is, this is the or radius I r, and this is I o, I r I and r o. So, now we have to done few checks. What are those checks? That means, the thickness that we have provided is sufficient or not, that checks we have to do. So, first checks is due for the buoyancy. So, for the buoyancy, that uplift force, or you can write this is the upward force due to buoyancy will be how much? So, that means the uplift pressure due to the buoyancy is H into gamma W. So, that you have to multiply with the base area. So, that area is pi r o square, okay, outside radius. So, this is for circular cross section or circular well, and Fu will be equal to, for rectangular it will be B outside into L outside, that is the area, into H into gamma W, that is for rectangular well. Rectangular well. Okay. Now, what is the downward force? F d is the downward force or the total downward force. So, that will be weight of the oil plus weight of the seal plus skin friction. Okay. So, what is skin friction? Because when there is a soil here and oil is placed here. So, there will be a skin friction between the soil and the oil. So, that force due to that skin friction is F Q. So, that is acting in the downward direction. Okay, why it will act in the downward direction? When this buoyancy force will try to push this oil in upward direction. So, the skin friction between the soil and the oil, that will act in the downward direction. So, that is why this Q will act in the downward direction. Now, this weight of the, or I should write in different color. Now, weight of this seal, that will act in the downward direction. So, this is the weight of the seal, and there will be a weight of the oil, that will also act in the downward direction. Okay, so, I should write weight of the oil, or WW. Okay, so, that means these three forces will act in the downward direction, and the force due to the buoyancy, that will act in the upward direction. So, that force due to the buoyancy F u, so that will act in the upward direction. So, buoyancy force will act in the upward direction, and due to that buoyancy force, there will be a friction will generate between the soil and the wall. So, that will act in the downward direction, that is Q. Then that now, the weight of the oil will act in the downward direction, and the weight of the seal, that will also act in the downward direction. So, I can write what are the different components. So, this where W is, here it is W is weight of the oil or cushion, Ws weight of the seal. So, this is weight of the seal. Then Q is equal to skin friction. Okay. So, for stability purpose, that F d should be greater than F u, such that the total downward force can nullify that upward force due to buoyancy. So, for the stability purpose, this F d should be equal to F u. Now, if F d is less than F u, then we have to change the thickness. So, how we will change the thickness? Then del T is the increase in thickness So, if F d is less than F u, that means the upward force is greater than downward force, then we have to increase the thickness of the seal. So, that amount of increase is equal to the difference between these two forces divided by the area of that seal, inside area of the seal, into the unit weight of the concrete, because the weight of the seal is equal to what? Weight of the seal is equal to inside area of the seal okay. So, this is the inside area of the seal into concrete into thickness. So, this is inside area of the seal okay. So, if this condition is not satisfied, that F D is not greater than Fu, then you have to increase the thickness by this amount. Now, the next check that we have to do is check for shear, What is that? That the shear stress that will develop, because there will be a buoyancy force which is acting in the upward direction. So, that means there will be and some downward forces will also acting. Okay, so, that means there will be a shear stress between the, or shearing will develop between this concrete seal and the shaft wall. Okay. So, that also you have to check whether that is sufficient or not, that the shear stress which is developed is the total shear force. First we will calculate inside the well. So, total shear force will be the shear stress that is developed into the perimeter, inside perimeter of the seal and thickness of the seal. So, inside perimeter the shear stress or shearing will develop the outside surface of the seal. Okay. So, that means here we can write the inside this perimeter of the seal into thickness into the shear stress that is developed. So, that will be equal to the shear stress that is developed due to the upward force, and that is A I H gamma W, that means the inside area. So, that is the force which is acting in the upward direction. So, that is the force which is acting in upward direction, and then A I T in the unit weight of the concrete. So, that is the force which is acting in downward direction due to the weight of the well. So, that means how these forces will develop. So, that means there will be upward force due to the buoyancy that will pushing this well in the upward direction, this thickness of the seal, I mean the seal in the upward direction, and the seal has its own self weight. So, that is acting in the downward direction. So, difference of these two will give you the amount of shear force that is developed within the inside perimeter of the well, okay, or between the seal and the shaft. So, that is equal to the shear stress that is developed. So, finally, tau will be the upward force due to the buoyancy minus downward force due to the seal divided by perimeter into thickness. So, this is the developed shear stress okay. So, now where I have already described the inside area of the seal or the area of the seal, because the seal does not have any inside or outside. You can say the inside area of the well, that is equal to the area of the seal, or this should be the area of the seal, or I should write this is inside area of the well. Okay. This A I. Similarly, the P I is equal to inside perimeter of the well and that is also equal to the perimeter of the seal. Okay, so that is equal to 2 pi r I for circular cross section, and equal to 2 into L inside plus B inside for rectangle. Cross section. So, this is the shear stress which is developed. So, the shear stress which is developed should be less than the permissible shears. Okay, so, that permissible shear is equal to tau ultimate, that is 0.175 root f c. Okay. So, which should be in mega Newton per meter square, where f c is in mega Newton per meter square, and we can calculate that phi, or we can take phi is equal to 0.85. Now, for the stability purpose, this tau should be less than tau u. So, that means we have to do these two checks to see whether the thickness that we are providing is sufficient or not. One check is the buoyancy force, which is acting in the upward direction. So, this buoyancy force should be taken care, and we will take care this buoyancy force, that weight of the well, weight of the seal, and the friction force. Okay. So, the weight of the well means, because that is the weight of the well without that seal, because seal is sealing is done once it is reached at the base of the well, or at the hard strata or the bearing strata. Now, in addition to the seal, the well has a shaft. So, that shaft has its own weight. So, those weight we have to consider. That means, this shaft has its own weight. So, that weight is the weight of the well, because in that situation only that shaft is present. Okay. Because after that, when the concrete is sealing is done, then there will be a sand filling, then there will be further concreting for that top plug. So, those things will be done later on, but when these buoyancy check is done to provide the sufficient thickness, at that moment there will be only that well shaft and the bottom seal. Okay. At that condition, we are checking whether that seal is sufficient or not, or that means that shaft weight and the bottom seal weight and the friction between soil and the well, that these three forces will act only in the downward direction to take care of the upward buoyancy force. So, that check is required, and another check is when there will be a buoyancy force is acting in the upward direction, and the weight of the well, that is also acting in the downward direction. So, that friction that will generate between the shaft and the concrete for the concrete for sealing. So, that friction that will generate should be within the permissible friction, and that permissible friction is given tau u, and this tau, which is the developed friction or developed stress between the shear stress between the well and the shaft. Clear? So, that means there will be a shear stress that will generate in this point between the shaft and the well, between the shaft and the seal, and there will be a buoyancy force and the weight. So, this shear that is developed, we have to check whether that is within the permissible shear or not. So, these are the checks that we have to do, and then if I start one example problem. So, I can give you the what is the example problem, and then I will solve this problem in the next class. So, this is a particular oil which has a circular cross section. Okay. So, this is the oil which has a circular cross section, and this is the HFL. The height of the well above the HFL is 3 meter. Okay. And then this one is the scour depth, and the this distance from the scour depth to HFL is 10 meter. Then the depth of the well is 8 meter, because 10 meter is the maximum scour depth, and as I mentioned that there should be 30% of that at least. So, 30% of that means around 3 meter, 3.5 meter, but here 8 meter is provided. So, that means it is okay. So, that means here this is 8 meter, and here the concreting is done, and this is the seal. So, that seal thickness we have to determine. So, this is the seal, fine. And then the properties are, so this is the at the, this is scour level, this is HFL, and the properties that this portion it is soft clay whose Cu is 25 kilonewton per meter square, and then it is resting on a bearing strata. Okay, this is stiff clay. Whose Cu is equal to 100 kilonewton per meter square. This is the center line. Okay. And this is the inside radius Ri, and this is the outside radius Ro. So, unit weight of water is taken as 10 kilonewton per meter cube. Unit weight of concrete is 24 kilonewton per meter cube. Then Ri inside radius is 2.25 meter, and that means the total inside diameter is 4.5 meter. Now, we have to determine what would be the thickness. Okay. So, this is circular cross section. So, that means it is passing through a soft clay layer of Cu 25 kilonewton per meter square and resting on a stiff clay layer whose Cu is 100 kilonewton per meter square. And the grip length is 8 meter, and then the other properties are given, and we have to determine what would be the thickness of the seal, and then we have to do those two checks that I have discussed. So, I will in the next class I will solve this problem, because this class I have given the input parameters. So, I mean those are the parameters or the properties of the soil are known for that particular open well. So, next class I will discuss that how we can determine the thickness of this seal. Thank you.